Hi again. Let's continue our study. First we had a break, so I just wanted to remind the points, main points of what was before. So we are studying the Dirichlet problem. Laplacian u equals f in some domain D, and u on the boundary of this domain is a given function g. So here we have some domain D and its boundary gamma. So we are solving this problem. Now, the general solution is the following for this problem. U of x equals integral over d g of xy f of y dy. Let me reduce a little bit this. Plus integral over gamma h of xy, g small of y, ds y. It is element of the n minus 1 dimension area. Yes? Here g is the Green's function which satisfies the following. Laplacian g of xy. G is a function of xy, so this is Laplacian with respect to y. Equals delta function of x minus y. So delta function at the point x, or y minus x, it's the same. First thing. And second thing, g of xy when y on the boundary is 0. So g is should be a function satisfying these two conditions. Now, in fact, to find this function, you see we have to solve some particular Dirichlet problem where f is delta function and g is 0 on the boundary. But in some cases we can really build this function g, this Green's function, and then we will be able to solve it. So these two cases, I will say it right now, are first when our domain is half space, yes, which is bounded by a plane. It is one case, and second, which we will study soon, it is when it is a ball. Yes, we are able to construct the Green's function inside the ball. Now what is h? H of xy equals the following thing. It is dg of xy d and y, y in gamma. And y is a unit normal, let me draw it here. It is d, it is gamma, this is the point y, and this is the unit normal vector n at the point y. So we have to take this same function g, it is the Green's function, and take its derivative in the direction of external unit normal at the point y. It will be our function h. So g is called the Green's function, and h is called Poisson function or Poisson kernel. Now, how to actually find them, these functions g and h, in the case when d equals r n plus. It is the set of x equals x1 xn, and we shortly write it x prime xn. X prime is the x1, x2 up to xn minus 1, and xn is looking up such that xn more equal than 0. So it is a half space. No, in case n equal 2, it is half plane. And in this case, we use the familiar method of reflection. Reflection method. Namely, for any point x equals, so x1 xn minus 1 xn equals x prime xn, so this is x prime. We defined x bar equals x prime minus xn. It is like y bar because this is notation from complex analysis where it is conjugate to a complex number. So it is also sort of conjugate point. And then we consider the following function. We have a function, fundamental solution, k of xy equals 1 over 2 pi logarithm module x minus y if n equal 2, 1 or 2 minus n omega n x minus y to the power 2 minus n if n is more equal than 3. Yes, this is fundamental solution. It solves the equation in the whole space. So delta y k of xy equals delta function at the point x. Yes? So this is a fundamental solution. But this solution does not satisfy the boundary condition. But now let us like g of xy equals k of xy minus k of x bar y. Yes? So it looks like follows. Sorry. So this is x prime, this is xn, x is xn, so Rn plus is this domain, just half space. So here we have the point x with column x prime xn, and the symmetric point x bar equals x prime minus xn. Yes? And if you consider this function, so the function kxy has a singularity at the point x as a function of y. And k x bar y has singularity at the point x bar, but x bar is beyond our domain, the upper half space. So inside this domain, this function is harmonic, k of x bar y. And if y is on the boundary here, the point y, then we see that the distance from x to y and distance from x bar to y are equal. X minus y equals model x bar minus y if y is in gamma. Gamma is this, gamma. It's this plane. And this means that this difference is 0. So it's the same idea as when we used when solving the Dirichlet problem for a string equation on half line. Here, instead of half line, we have half space. So this is the Green's function. We have already found it. Now, having this expression, we can find also the Poisson function h of xy equals, here was one subtle moment. It is the derivative of this function gxy when y equals 0 in the direction of unit external normal. But unit external normal vector looks outside, so it looks down. It is ny. It is the point y. It is vector n at the point y. And it looks down, so it is d g of xy dny when yn equals 0, so y is on the boundary, and it is opposite to the derivative with respect to yn, which is equals minus dg xy dyn when yn equals 0. Now, last time I performed this simple calculation and found the following thing. H of xy equals, the general formula is 2 divided by omega n xn module x minus y to the power n. Yes? Omega n is the area of a unit ball, a unit sphere, this n minus dimensional area of unit sphere in the n-dimensional space. Now, in particular, for n equals 2, we have the following formula. h of xy equals 1 over pi x2 divided by x1 minus y1 square plus x2 square. Now equals 1 over pi x2 divided by module x minus y square. So in this case we have to look at this picture literally. We are in the two-dimensional space, that means in the plane, and we have this especially simple function. No, it is simple but not trivial. So I wanted to discuss it a little bit before going further. So, if we solve the equation delta u equal 0 in R n plus, u on the boundary R n minus 1, which is gamma, equals g of y prime. Y prime because yn equals 0. So we solve this particular Dirichlet problem, and solution looks as follows: u of x equals integral over R n minus 1 g of xy h of xy g of y dy, dy prime in this case. So it is n minus dimensional space. Now in case of plane it is the integral over the line. Now in particular, suppose g of y equals delta function of y minus y0. So it is unit mass at some point. Why not? So if you can have delta function in the right hand side for the Green's function, why don't we have delta function in the right hand side for the boundary condition? And let us substitute here u of x equals integral over gamma h of xy delta y minus y0 d y prime. What does it mean? Integral of function, no side, continuous function, times delta function at some point. We know what it is. It is value of the function at this point. So it is equal to h of x y0. Yeah? So, you see, if we have this situation, this is the point y0, and the boundary condition is so it is 0 here, 0 here, and here it is delta function, yeah? Now we can imagine it approximately like this. Yes? Delta like, and then limit when the width of this delta function, this function goes to 0 and the height goes to infinity, and the integral remains 1. Yes? Then the solution is given by this function h, the Poisson function. Very good. So this is the meaning of Poisson function. If Green's function is a result of solving equation with 0 on the boundary and the delta function at the point x at in the right hand side, then a Poisson function is a result of solving this problem when Laplacian is 0, so it's a harmonic function, but on the boundary it is a delta function at some point. Now we can, in this case, for example, we can look how does this function behave when you are approaching the plane. In this case, the line x2 is 0. Let me a little bit. So it is, say, y1, the function of x, no, x1, x1, x2. This is the point, say, y0. And the function is given by this, h of x, y equals h of x1, x2, y equals 1 over pi x2 x1 minus y1, in this case y0, if our square plus x2 square. So this is our function. Now what happens if you are approaching the axis x2 equals 0, x1 axis at some point? Then numerator goes to 0, x2, and denominator, if x1 different from x2, it is x1, different from y0, then this term is positive and constant. No, this also goes to 0, but this term saves the situation. And this means that limit when x2 goes to 0, I draw this, so goes to 0, and from the above, h of xy equals 0 if x1 different from y0. Otherwise, if we are going this way, x1 equals y0, then you have this term is 0, and you have x2 divided by x2 squared, 1 over x2, so it is infinity if x1 equals y0. But if you consider what happens on the line, this is if you go individually for one individual x1. But consider how behaves this function when you consider the line x2 equals epsilon. No, epsilon, it is small, so we can see what happens when epsilon goes to 0. Then h x1 epsilon y0 equals the following. If you substitute here 1 over pi, x2 it is epsilon divided by x1 minus y0 square plus x2 is epsilon square. Yeah? So you see the following thing. When x1 minus y0 is positive, then this goes to 0, and uniformly, let me write it. H of x1 epsilon y0 goes to 0 as a function of x1 epsilon and y0 are parameters. When epsilon goes to 0. Epsilon and y0 are parameters, so it goes to 0 uniformly if x1 minus y0 are more than some constant a for any positive a. Yes? So if you consider this domain y0 plus 8 is y0 minus a, beyond this interval, here and here, it goes to 0 uniformly. Yes? And here something happens, but what exactly happens? What exactly happens here? There are two ingredients of delta function. First, it is 0 everywhere but one point, and second, that its integral equals 1. So we have to consider integral of this function. Integral, say, from minus infinity to plus infinity. 1 over pi. Integral of what? Epsilon divided by x1 minus y0 square plus epsilon square dx1. Yes? So let us write it is epsilon let us write that it is 1 over pi epsilon integral dx1 x1 minus y0 square divided by epsilon square plus 1. Yes? And now we introduce new variables z equals x1 minus y0 divided by epsilon, dz equals dx1 divided by epsilon, dx1 equals epsilon dz, and this our integral I equals 1 over pi epsilon integral dz epsilon dz divided by z square plus 1 from minus infinity to plus infinity. Now this epsilon and this epsilon cancels, equals 1 over pi integral dz z square plus 1 from minus infinity to plus infinity equals 1 over pi arctangens z from minus infinity to plus infinity, but arctangens changes from minus pi over 2 to plus over pi over 2. So this is pi divided by pi, so this is 1. So, okay, we have, when epsilon goes to 0, we have a family of the functions which have very high spike at the point y0, yes, and here everywhere it goes to 0, and integral along along these tails also goes to 0 if you integrate beyond any finite interval containing y0, and the integral of delta of this function overall is 1. So the function concentrates when you approach the axis x0, the function concentrates at one point. All its mass concentrates on one point, it's equal to 1. So this function is a true Poisson kernel, Poisson function. So this is what I wanted to say about this function for now. So in the next part we consider a similar construction for the ball. For now, have a good time. Bye. Okay. Hi again, glad to see you. Now we consider Green's function. And Poisson kernel in a ball. So we have a ball. Of radius r, and we solve, no, gamma is the boundary of this ball. Radius r, let us fix it. And we are solving again the problem. Delta u equals f in B, u on gamma equals g. Again, the Dirichlet problem. here it turns out they also can use the reflection method. But here it is a little bit more tricky. So reflection here, we have to somehow make reflection relative to the sphere. It is not the same as reflection in the spherical mirror. Yes, it is called not reflection, but it is called inversion. So what is inversion? We consider a sphere, consider it is center O, yeah, sphere of radius r, and consider a point x. And for this point we consider the point x bar. Let me denote it again, x bar. So which is lying on the same line, on the same ray as x relative to the center, but module x bar equals r square divided by module length x. Now, if we consider corresponding vectors from O to x and from O to x bar, so I identify the point with the vectors, then we can write that x bar equals r square divided by module x square x. So this is a sort of transformation of the space. Now if x lies on the sphere, then its module x equals r. So this factor becomes 1. Yes, and so the sphere itself is fixed, consists of fixed points of this transformation. So this transformation sort of turning the space inside out. The inner part of the sphere is transformed into outer part, the outer goes to inner part. Now as we approach the center of the sphere, then the inverted point goes to infinity, no, and back. If the point x bar goes to infinity, or x goes to infinity, then x bar approaches the center of the sphere. So it is the inversion. And you know what? The calculations are identical in all dimensions, no, practically the same. So if you don't mind, I will perform all calculations for n equal 2 in the plane. Yes, and then just write you down the formula which is good for any dimension. Just because the I would say idea is the same. So suppose we are in the plane. And suppose we have 2 points which are, say, inverse of one another. So one point is here, it is radius r, it points at the point A, the distance OX equals A, the inverted point x bar, this point is B, so module x times module x bar equals r square. Yeah. So module x bar equals r squared divided by module x. And now consider any point lying on the sphere. In this case, sphere is the circle of radius r, say point y. And then we have a beautiful geometrical theorem that if you consider the distance between x and y and between x bar and y, then you have module x bar minus y divided by module x minus y equals constant. Circle is gamma. If y in gamma. Yes, so this is a geometrical property of inversion, which no should be proved. Let us prove it. So we find this and we find this, and then find that the ratio is independent on the point here. So the point x equals a0, y has coordinates b0, b equals r squared divided by a. Now the point y equals r cosine theta, r sine theta. Let me take this representation. And now let us find x minus y. X minus y equals a minus r cosine theta minus r sine theta. X bar minus y equals b minus r cosine theta minus r sine theta. Yes? Now, module x minus y square, I want to avoid square roots, equals a minus r cosine theta square plus r sine theta square, because it is square, equals a square minus 2 a r cosine theta plus r square sine square theta, cosine square theta plus r square sine square theta equals a square minus 2ar cosine theta plus r square. Yeah? Module x bar minus y equals b square minus 2b r cosine theta plus r square. No, the same way I found this. Now I have to transform x bar minus y square, equals, what is b? b is r squared divided by a. r4 divided by a square minus 2 r square over a r cosine theta plus r square. I wanted to, it is the following, so it is r square a square, so it is r square minus 2, so a r, yeah, cosine theta plus a square, yes, that's it. But it is equals r square a square x minus y square. Yeah, if you follow this, you see this. So module x bar minus y equals r over a module x minus y. Equals r over module x minus y. Here x is is a fixed point, yes. X is a fixed point. For each fixed point x, you see that the ratio of x bar minus y and x minus y does not depend on y, depends only on x. Length of x, or distance from 0. So we have this, now we have it. And now we can see that if you take the function g of xy equals, no, in case n equals 2, let us work in this. So first of all, the fundamental solution k of xy equals 1 over 2 pi logarithm of difference between x minus y. Yeah, we have already this function. And now let us write g of xy equals 1 over 2 pi logarithm module x minus y minus logarithm module x bar minus y. And if you take this difference, it is logarithm of ratio x bar minus y to x minus y. Well, let me write it. X bar minus y, x minus y equals r over modulo x. Yeah. So on the circle of radius r, this ratio is constant if x is fixed, so logarithm is also constant. Logarithm of this difference of logarithm is logarithm of ratio, so it's also constant. So we simply have to subtract logarithm of this minus logarithm of r divided by modulo x. So this function has, for any fixed x, this function has a singularity at the point x as a function of y. Yes, first thing. Second thing, it is harmonic beyond the function y. So delta y g of xy equals 0 for y different from x. Yes, and g of xy for y on gamma equals 0. Yes. So this is the Green's function. That's it. That's it. In the case of n more than 2, we have similar things. That if you take the point x and inverted point x bar and take the distance to x, from x to y and from x bar to y, on the sphere it is constant. Yes? So we have to take the function fundamental solution with singularity at the point A minus fundamental solution with singularity at the point B, but multiplied by some factor, the ratio between the distances to corresponding power. Let me show it when I finish with n equal 2. Then I will reproduce it for any other dimension. So for now we stay with n equal 2. And now I wanted to consider the boundary condition, and for the boundary condition to take them into account, we have to find the Poisson kernel. So h of xy equals dg of xy d and y when y is on the circle. Now again we have to calculate it. So this is our circle. Here we have point x. Now let us put it here. It is x bar. And here the point y. So this is the point the radius is r. So how to find this derivative? Let us do the following. Consider the point y of r equals, no, the point is moving with unit speed, equals r cosine theta, r sine theta. Yes? And we honestly find the derivative dr g of x, y of r. Yes, where g is given by this. For r equals r capital. So when we reach this point, it will be exactly derivative of the function g with respect to the unit external normal. So for this we have to honestly write g in coordinates. G of x1, x2, y of r equals 1 over 2 pi logarithm of x minus y, it is 1/2 of logarithm x minus y square. 1/2 logarithm x1 minus r cosine theta square plus x2 minus r sine theta square plus minus 1/2 logarithm x x bar, it is r square divided by module x 1 minus r cosine theta square plus, one moment, I'm sorry. A, B. So it is x bar. X equals A0. X bar equals B0. B equals r square over A. And so G of xy equals 1 over 2 pi 1/2 logarithm a minus y1 square plus y2 square minus 1/2 logarithm b minus y1 square plus y2 square and minus logarithm of r divided by a. A is model x, which is equal to, let me write, g of x, y of r equals 1/2 pi 1/2 logarithm a minus r cosine theta square plus r sine theta square minus 1/2 logarithm b minus r cosine theta square plus r square sine square theta plus or minus logarithm r over a. Now, after we can a little bit simplify what is in the brackets. So it is equal 1/2 pi. Let me write 4 pi. 1/2, let me put it here out. Logarithm of a square minus 2ar cosine theta plus r square minus logarithm b square minus 2br cosine theta plus r square plus some constant c, which will disappear because I'm going to differentiate it. So d dr g of x y of r. Now we have to differentiate this with respect to r equals 1/4 pi. Here a square minus 2ar cosine theta plus r square, and here will be minus 2a cosine theta plus 2r minus b square minus 2br cosine theta plus r square, and here minus 2b cosine theta plus 2r, and this constant gives 0. And which is equal to, here denominator is equal to r squared divided by a squared. We have already found it. If you substitute here b equals r squared divided by a, we have this with factor r squared divided by a squared. So 1 over 4 pi minus 2a cosine theta plus 2r divided by a squared minus 2ar cosine theta plus r square minus a square r square, and and here we'll have minus b cosine theta plus 2r divided by the same a square minus 2ar cosine theta plus r square equals 1 over 2 pi after all, because here b equals, if you substitute here, the result will be the following. Minus a cosine theta plus r plus a cosine theta plus a square r square r divided by a square minus 2ar cosine theta plus r square. Oh my god. And now we have to substitute here, just a minute, it is in the numerator. We have to substitute here r equals r, capital. Then what happens? First of all, this and this cancel. It is so here we have r capital, here a square divided by r. Just a minute. Minus. It's important. So d dr g x y of r, or r equals r capital, equals, so what is 1 over 2 pi, and here we have r minus a square divided by r, r square r, yes, and in the denominator is a square minus 2a r cosine theta plus r square. And what remains here? Equals 1 over 2 pi. Let us put this r here. Then here 1 minus a square divided by r square. And here we have a square minus 2a r cosine theta plus r square. And in our picture, is A, it is angle theta, it is the point Y, the radius is R, and what is appears here, it is simply the distance between this point X and the point Y, module X minus Y square, equals, this is this distance is r cosine theta minus a square. It is this, and this is wait, cosine plus this is r square sine r square sine square theta, which is equal to r square cosine square theta minus 2 r a cosine theta plus a square plus r square sine square theta equals cosine square plus sine square is 1 equals a square minus 2r a cosine theta plus r square. It is exactly what we have in the denominator. And so the final answer is the following. H of xy equals 1 over 2 pi r 1 over 2 pi r 1 minus a square over r square divided by module x minus y equals no, r was here after all. Yes, r. And now equals, if you multiply it by r square, then 1 over 2 pi r, and here is r square minus a square divided by module x minus y equals, what is a square? A square is module x square. 1 over 2 pi r, r square minus module x square divided by module x minus y square. Whew. No, for example, okay, we found this function h of xy. So again, if you are solving equation delta u equal 0 in our domain B, no ball or in the disk, and u on the boundary gamma equals g of y, then u of x equals integral over gamma h of xy g of y d s, no, in the case n equal 1, l equal 2 dl y, length on the circle. Consider example. G of y equals 1 first, and x equals 0, so it is the center. Yes. Then let us try. U of x equals integral along gamma h of x y, g of y is 1, d l y equals our contour gamma is a circle of radius r. Yeah, so equals integral from 0 to 2 pi h of xy. It is here 1 over 2 pi r. R square minus module x square, it is r square, divided by x minus 1 equals x minus y. X is here and y is here, so it is r square dly equals integral from 0 to 2 pi 1 over 2 pi r. R here is 1. What is dly? It is r d theta. No equals 1. Okay, let's consider this situation. Harmonic function which is in the circle, which is identically 1 on the boundary, is just constant 1. No, because constant 1 is certainly a harmonical function. Constant is a harmonical function, it's one thing. And second, we did not prove it yet, but we will prove very soon that solution to this problem is unique. So if it is unique, then we are done. And it is just a simple check of our formula. Yeah. Now, again, let us look at this function where it is. So h of xy equals r square minus module x square divided by module x minus y square. So if you are in the circle, x is here, so y is here, and x is somewhere here. X is inside the circle and y on the circle. Then what happens when x approaches to the circle? Then module x square is approaching r square, so the numerator goes to 0, and the denominator depends on where we are. If we are going to some limit point on the circle which is different from y, then this is positive and doesn't go to 0. So the limit is 0. If we are going to the point y, then here the limit is one moment. 1 over 2 pi r, of course. R square minus module x square divided by module x minus y square. So when we are moving here, so x is here, then x minus y, r square minus module x square is minus module x square equals r minus module x, r plus module x. So this goes to 2r when module x goes to r. This goes to 2r, this goes to 0 as r minus module x. So numerator behaves like r minus module x. No, in fact, 2 times r minus module x. Denominator is, if you are going along the same radius as y, then denominator is r minus module x square, because of this square. Yes? And so this all goes to infinity. And then we have to analyze this formula. So what should we do? We have to consider, so this is point y, and let's consider a smaller circle, or this circle of radius r minus epsilon, and consider how does this function, which is written here, behave when x is on this smaller circle and goes, so how does it behave? It turns out from this formula, when epsilon goes to 0 and we are outside a small segment of some arbitrary small length but constant containing y, then here this function goes to 0 uniformly, because denominator is bounded off 0 and numerator goes to 0 as r minus module x. And the last thing which requires a little bit integration shows that integral over the whole this circle of radius r minus epsilon of this function is always identically 1 for any epsilon. Yeah? So this means that this function, which is written here, if you consider it on this circle, also behaves like this. Here it is very small, and here it has very high and narrow peak. And the integral is 1. So it is again delta-like function, and when epsilon goes to 0, it tends to some delta function. So this function is a solution of the boundary value problem, where instead of g of y we have delta of y minus y0. Yes? So it is delta function at the point y0. That's it. So this way we found this function, and then we will extract different implications of these formulas, and we can learn a lot about the harmonic functions from this formula. In fact, it is a very particular but very important case. For now, let's finish. Have a good time. Bye.